Swayam Prabha. Digital India. Educated India.
So, I will define this. So, a Nash equilibrium is simply this. So, a Nash equilibrium is simply B1 star to Bn star such that Ji of B1 star to Bn star is less than equal to Ji of Bi comma B minus I star for all Bi and for all players I. Okay. And a Bayesian Nash equilibrium is this kind of wait and watch equilibrium. Is a B1 star to Bn star such that Ji of B1 star to Bn star given Ti is less than equal to so Ji of B1 star to Bn star is less than equal to Ji of Bi comma B minus I star given Ti for all Bi and for all types Ti in Ti and for all players I. So, what is the difference between the two? The difference is that should this game be, when I asked should this game be played here and should this game be played here, what is the difference? The difference is that here in the, above the strategies are being chosen before the types get realized, alright. Of course, the strategies are functions or are behavioral strategies, so they are planning for every possible type. Okay. Here the strategy itself is being, although it is of course making use of the type information, but it is being chosen after the type gets realized. But your own type only, remember, not the type, you do not know the types of the others, alright. So, that's why that is the subtlety. Now, it turns out actually that once you think about it clearly enough, actually this collapses very nicely and we can, it turns out that it is not that hard to see that these two are in fact the same. Okay. So, there is, let us define this form called the agent form. Okay. This has other names also, some people call it extended form or whatever. So, in the agent form what happens is, see, I will give you an intuitive picture. See, essentially remember we have like in the terrorist example, security example, you had three possible types for the traveler. He could be a terrorist, he could be a smuggler, or he could be innocent, right. So, there are these three possible types of the traveler, and in each case once his type gets realized, he is one of the three, right. So, as a security officer, what I am doing is I am actually playing not against one player, but rather three different players. So, each type of each player is essentially a distinct sort of persona or distinct entity. Okay. So, once you realize that, essentially it is like, essentially once you know the type, you are a distinct player, right, because after that the tree splits. And what a player knows his own type but does not know the types of the others. Okay. So, what you can create is this, what we call an agent form, in which every type of every player becomes a pseudo player. Okay. Okay. And so then when you look at these equations, then these equations which look like a kind of a strong form of the Nash equilibrium is essentially now a Nash equilibrium strategy that each type of each player is playing separately. So, these are now equations for all Ti and for all I in N, right. So you club these to every type of every player if he is a distinct player. So then it's like a Nash equilibrium but with a larger set of players. Okay. So this is basically the key idea, and that gives us everything that we need. So let's just write these things out. So first let's an agent form is essentially has union of Ti players. Okay, and so that means the number of players is summation size of Ti. So the actions for player I is this. For player for player Ti is this. Now I can just index players or identify players with just the type name, right. So for the actions for player Ti is now AI of UI of Ti. Okay, and what is the what's the payoff that this guy gets? He gets Ji of so here let me write an action profile U. Okay, now this is a fixed action profile for actions of all summation Ti players. Now I want to write the cost of player Ti when all players have chosen this action profile U. Okay, so this is going to be what I would get, what player I would get in when these actions are chosen. So if you remember, we had this, where is this here, right? When these actions are chosen in a certain type profile, right? So this is T comma U, and then I take P of T minus I given Ti, and you do summation over T minus I. Okay, so assuming others have taken an action, if assuming an action profile U taken by all the summation Ti players, you just average out this, take the average by doing a conditional expectation over T minus I. Okay, this now defines for you a payoff for type I for player I's type I, which for us is player Ti. Is this clear? Okay, and now what you can show is actually this theorem. So this theorem is that a Bayesian Nash equilibrium is equivalent to a Nash equilibrium of the agent form. Okay, so the Bayesian Nash equilibrium effectively, just as I said, it's as if there are summation Ti players here, because this is being written for every type of every player. So it effectively becomes this reduces to the Nash equilibrium of the agent form. Okay. Now this theorem is actually not that important for us to prove, but what we will prove today is this one, which is, so this was by Harsani in 1967. Okay, and so this Bayesian Nash equilibrium is equivalent to a Nash equilibrium. So the Nash equilibrium that we defined where players are, which is this one here, which is defined at the, where strategies were chosen at the start of the game, is equivalent to this, where strategies are being chosen after the types get realized. Okay, all right. So let's just quickly do the proof of this, not that hard. So first let's show this Bayesian Nash equilibrium is also a Nash equilibrium. Okay, so let B star. So by the way, I forgot to mention, since I am going to be dividing by probabilities like this, I have to assume that all probabilities are positive. Okay, so no division by 0 and all that stuff. Okay, so let's not worry about those things. So, P is always for all types. Okay. Let B star be a Bayesian Nash equilibrium. Then for each I in N, so we have assuming B star is a Bayesian Nash equilibrium. So, I have to look at this B star given Ji of B star given Ti now, okay, because I am conditioning on Ti. This is less than equal to Ji of Bi comma B minus I star given Ti. Okay. Now, suppose the now this is a behavioral strategy. Okay. So, given the type, I am choosing a pure strategy. Okay, for each type. So, there are okay, again I did not mention this, but again there are finitely many pure strategies for the player. Finitely many pure strategies, which means that when I write this over all Bi, so this has to be true for all Bi, right? This has to be true for all behavioral strategies Bi, which means in particular it is true for all pure strategies. Okay. So, if I have actions, so in particular this means that this is less than equal to this here. This is true for all actions Ui that player I could take in this type. Okay. Now, for take any pure strategy gamma I that maps, take any pure strategy gamma I, I do not want to write too much. Okay. Now, what is the payoff under that pure strategy gamma I while others play B minus I star, and this is the payoff, this is the ex ante payoff, okay, before the start of the game. Okay. So, what is this equal to? This is equal to now, does everyone see this? So, here is the payoff that I am writing, form a pure strategy gamma I, okay, where the others play B minus I star, behavioral strategy B minus I star. Now, when I say play pure strategy gamma I, essentially it means that I am going to take an action gamma I of Ti when my type is Ti, alright, and that is when I take that action, okay, the payoff that I get is this thing here, alright, and then I am averaging by taking expectation over Ti, alright. And now, what is this quantity here? Well, this here, this quantity here is actually present here, right. So, this guy is in fact greater than equal to P of Ti Ji of B star given Ti, and this is therefore Ji of B star, right. So, what did we just prove? We just proved that Ji of B star is less than equal to Ji of gamma I comma B minus I star, right. So, then now what do I, well, this is true for every gamma I. Now, since this is true for, this is true for each gamma I, that implies that Ji of B star is less than equal to Ji of Bi comma B minus I star, B minus I star for all Bi, which means that this is a B star is a Nash equilibrium. Okay. So, in short, if you take a Bayesian Nash equilibrium in which players are choosing the strategies after knowing their types, okay, then that you average the whole thing out and you get a Nash equilibrium at the ex ante Nash equilibrium. Okay. Okay. So, it's the reverse that's a little bit more interesting, right. So, now what we will want to show is this Nash equilibrium is every Nash equilibrium is a Bayesian Nash equilibrium. Okay. So, suppose B star is a Nash equilibrium, but not a BNE. Now, suppose it is a Nash equilibrium, but not a Bayesian Nash equilibrium. Okay, then what would happen? If it is a Nash equilibrium, but not a Bayesian Nash equilibrium, now think about the agent form. That means there is going to be at least one type of one player who would want to deviate from B star, right. So again, essentially in a Bayesian Nash equilibrium, there are summation Ti many players. So if this is not a Bayesian Nash equilibrium, then there is going to be in some case, that means at least one type of one player, there is going to be an incentive for deviation. Okay, means there exists at least one I and a Ti in capital Ti and an action for that player. So, and an action Ui in Ui of Ti, such that action gives you better payoff than the star value payoff. So, that means this Ji of given Ti, this is strictly greater than this Ui Now, why did I reduce this to actions? See, if actually there is at least one behavioral strategy in the, or at least one probability distribution on the actions that gives you better. But once there is a probability distribution that gives you strict inequality, it means that there is at least one pure strategy that is going to give you strict inequality, right? That is what it would mean, because the probability distribution is just averaging over the pure strategies after all. So that means there is one action for this player in this type which gives you a strict inequality. Is this clear? Okay, so this is less than this. Okay, so now again go back and think about just the way we had we had argued in this informationally inferior games and so on. So now if there is a better action that you could take in some type, and the type was known to you, then what could you do? Then you could take that action even before the type was known to you and put that as part of your plan, right? This was the same argument that we used. So essentially, with this additional information of the type, if there was an action that you could take, okay, which was better, okay, which is better for you once the type gets realized, you could take that action, incorporate that action in your plan even when you did not have the information of the type, right? And that's exactly how we showed that equilibria of inferior games carry over as equilibria of richer games. If there was if there was some place a player could take a better action, you started off with exactly this sort of premise, right? We said, suppose there is an equilibrium of the inferior game which is not an equilibrium of the richer game, which means that there is some deviation possible in once you have some additional information. But then if there was such a deviation, then you could plan for it, and you could plan for it and play for it even when you did not have that information, right? So same sort of logic here. So if there was an action that you could take which is strictly better than this B star, that gives you a payoff strictly better than this B star payoff, then you could have taken that action as part of your plan and come up with another strategy before that information actually comes to life. Okay, so now consider, so that's exactly this construction here. Consider B hat I, okay, of, so this guy what it does is it mimics B star I for all types except for this particular one. So let us call this Ti dash, okay, for all Ti dash not equal to Ti. So that is this special type where you had the deviation. For all other except for that type, you are just mimicking what you did in the starred strategy. And once you get to this type where there is a deviation possible, you take the action that was that supposedly is better, right? This action which is better, you take this action. And now under this is now another behavioral strategy, and under this behavioral strategy you can compute the payoff that you can compute the payoff that you would get even if you did not know the types. So you get B hat I comma B minus I star, you take this summation of P of Ti Ti dash, let us say, this Ji of B hat I B minus I star given Ti dash, and let's just write this out. This is Ti dash not equal to that special Ti in which case when it is not equal to, you are just playing, it is the same as doing B star. And when it is equal to, you do P of Ti and you take that special action Ui. Alright, and this guy becomes now strictly less than J of B star by using this is just by using this particular thing, this using this strict inequality here. So, the thing I am using again is as I said, we avoid pathological cases. So, because I get a strict inequality because all the probabilities are positive. Okay. If one of the probabilities becomes 0, a lot of pathologies emerge and so on. So, we those kind of corner cases, I mean they are interesting, but interesting more mathematically than than for the underlying logic of games. So, that is not such a big attraction for a separate study. So, which would mean then that B star is not a Nash equilibrium, okay, a contradiction. All right.